The railway through the Welham Green curve between Welham Green and Hatfield stations has 4 lines. It was on the down-fast line at 12:23 on Tuesday the 17th of October 2000 that this curve, half a mile from Hatfield station, would become infamous. The 12:10 Great North Eastern Railway service from London King's Cross to Leeds was travelling at between 115 and 117 miles per hour as it came round the Welham Green curve. Hauled by a single locomotive, on that Tuesday it was carrying 170 passengers and 12 members of staff across 6 standard-class coaches, 1 buffet car, 2 first-class coaches and a driving van trailer. As the train traversed the curve, the wheels of the first locomotive and following 2 coaches passed over a section of rail with no issue. However, under the 4th car, Car C, this rail fractured and then fragmented completely into over 300 pieces. The underside of some of the train cars were found to have scars and other damage consistent with being struck by fragments of the rail, showing the forces unleashed as the rail disintegrated. The locomotive and first 2 carriages, coaches A and B, continued on down the track, but the rest of the train, starting with coach C, derailed with varying degrees of severity. Coaches C, D, E and F, while in the process of derailing, increased the damage to the rail, the fragmentation and its dispersal across the site. These coaches, apart from coach F, although derailed, remained basically upright and on their wheels. Coach C struck and dislodged signal Kilo 563, while coach F came to rest with an approximately 70-degree lean. The service car, coach G, then came into the area of the fragmented rail, further damaged by the previous 4 coaches. As this coach derailed, the bogies, or wheel sets, detached from the rest of the coach structure. This, along with the other forces involved, caused the service coach to overturn onto its left-hand side, swinging out to the left of the track and coming into contact with nearby overhead line masts at the side of the track. The mast was uprooted from its base and went through the roof of the service coach. The service coach carried on down the track, coming into contact with a second OLE mast, which in turn also became embedded into the coach. This second mast did considerably more damage, penetrating down from the roof to the level of the tables, seats and floor. From paint marks found on the site, left by the blue paint from the side of the coach, it seems that the service coach overturned very soon after coming into the derailment zone. Coach G came to lying on its left-hand side with considerable damage. This overturning also led to the coupling to the first coach behind, coach H, braking. It also separated the pneumatic brake connectors, which led to the brakes being applied. The train was now split into 2 sections. As this second section entered the derailment zone, which was already considerably damaged by the first section of the train, first 2 of the 3 coaches embedded deeply into the ballast. This caused them to rapidly decelerate, which in turn led to overloading of the coupler, further separating the train into 3. Coach H came to rest with a 70-degree lean into the trackside bushes. Due to the rapid deceleration caused by the contact with the ballast, this was 245 metres behind the service coach, coach G. 5 metres behind coach H, the second first-class coach, coach M, and the DVT came to rest. Both were fully derailed, but standing upright. The diagram on screen shows the final locations of the 9 coaches and the locomotive that comprised the 1210 GNER service. The train guard and driver used mobile phones to report the derailment. They then took steps to protect the train from collision by another train travelling through the area, a very real threat in an emergency situation. With the damage to the overhead line mast from the service coach, the overhead lines were also brought down. Within 10 minutes of the derailment, the first emergency services arrived at the site and assisted with the evacuation already started by the train staff, as well as attending the many injured. 4 passengers were killed and over 70 injured, 4 seriously. The British Transport Police then took over the site, where the job of preserving evidence and identifying the causes started. So what caused the rail to fragment and disintegrate into hundreds of pieces under a train? An overwhelming majority of the rail fragments were recovered, and this allowed a large section of the rail to be reconstructed in the lab after the incident. On-site findings, confirmed in the lab, put the cause down to extensive fatigue cracking, known as rolling contact fatigue, or RCF. Rolling contact fatigue defects are initiated on or very close to the surface of the rail, caused by the large and concentrated forces at the rail-wheel interface. This stress causes cracks on the rail surface that grow due to the repeated cycle of passing wheels. The cracks can either grow across the surface of the rail, leading to shelling or spooling defects where the material appears to flake off, or they can grow down into the rail head, known as a transverse crack. If left, these transverse cracks can lead to sections of rail breaking away, or the rail breaking completely. The type of RCF defect that occurs depends on a large number of factors, including the rail material characteristics, environmental track conditions, and track geometry. Both spooling, the localized detachment of metal from the railhead, and transverse cracks across the railhead and down into the body of the rail were present at Hatfield. Investigators noted that some areas were dark and oxidized, showing they had been present for some time, while others were bright and shiny, indicating they had occurred recently. In sections of rail from the north end of the derailment site, 3 complete transverse fractures of the rail were found. These are shown on this side sketch, which details the key locations in relation to the rail. Testing on these cracks suggested that one of these rail breaks had occurred at the time of the derailment, while the other 2 had occurred some time prior. Other evidence supports this, such as a wide running band, which is the polished area where the wheel contacts the rail, around these 2 fractures, along with issues experienced with the track circuit signalling system prior to the derailment. However, these breaks were away from the initial point of derailment, so were not the primary cause. Even after extensive testing on site and laboratory work, it could not be identified which part of the rail was the first to fracture. Lab tests for hardness, tensile strength and chemical composition indicated that the rail complied with the existing standards for Mill Hill treated rail, the type of rail at site. MHT rail was a rail type developed for improved resistance to wear. The lab did notice there was less surface cracking and spooling in the areas around the flash butt welds used to create the long rails used during renewals. They also noticed that, within the microstructure of the rail, near the surface, there was a 0.4mm layer of ferrite, a type of microstructure, within the material of the rail. This layer was softer than the rest of the rail, and likely caused by surface decarbonation occurring during the manufacturing and heat treating processes. In other tests, it had been noticed that the rolling contact fatigue performance of MHT rail was reduced significantly in the presence of decarburization. Why did these areas around the welds have less RCF? Following welding, grinding was undertaken to ensure a smooth running surface. This also removed the layer of ferrite, the area where RCF cracks were initiating and growing from. So the root cause of the rail fragmentation and disintegration into hundreds of pieces was extensive and severe rolling contact fatigue defects, aided minorly by the presence of a ferrite layer on the surface of the rail. But how was the rail allowed to get into such a state? A report by the Rail Safety and Standards Board found a number of underlying causes. These causes were an incomplete appreciation of the risks of RCF. While testing and investigation of the rail was being undertaken, the Health and Safety Executive commissioned a study into the effectiveness of the ultrasonic testing procedures used at the time. It found that these had been adapted or adopted from procedures used to find other defects, not specifically RCF. So while they were broadly suited, they could only reliably detect RCF cracks that were deeper than 5 to 6 millimeters and in the range of 15 to 25 degrees in angle. This meant that specific processes for managing RCF were not up to the level of other defects. It also found that patrollers and other staff lacked the training around RCF and its risks, which meant they didn't react to it in the same manner as other defects. In the build-up to the derailment, starting around a year earlier and then accelerated after a rail break at Aycliffe, changes were made to how RCF was tested, along with the actions taken when the defects were found. However, we will see that although at a high level actions were taken, there were still issues on the ground. Failure to manage a visual and ultrasonic inspection regime to establish the true condition of the rail at the Welham Curve. The railway standards require sections of track to be visually inspected by patrolling staff at regular intervals to identify issues and faults. These are then reported to management so their rectification can be planned. This basic level of visual inspection, however, was not occurring at the Welham Curve. Because of staff shortages and safety concerns, the patrollers carried out their inspections from the edge of the track, rather than the forefoot as required by the standard. Records also show that all 4 lines were being inspected in a single patrol, rather than a maximum of 2 as per the standard. Patrolling staff made no reports on the railhead condition in the lead up to the derailment, despite the terrible condition of the rail. Investigators also found that inspections by various levels of management, undertaken at less frequency, were below the number and frequency required by the standard, and when they did occur, nothing about the railhead condition was noticed. When it came to the ultrasonic inspections, managed by a separate team due to the specialist nature of the equipment and procedures, the picture painted by the report was not much better. No annual inspection plan, as required by the standard, could be produced. While general testing was happening at the required frequency, the tests specified in the standard to be carried out when a defect was found were not being undertaken. This was then further compounded by the fact that defects were either not categorised at all or were done so incorrectly. This categorisation, which depends on a number of factors such as size and severity, gives a minimum action required to be undertaken. This includes a mitigation, such as speed reduction or applying clamps to the rail, if required, along with a time frame for the defect's removal. The defects on the Welham curve were continually retested, but were not subjected to the correct mitigation actions, such as speed restrictions. One reason for this highlighted in the report was that staff were not briefed on the new requirements brought in after the Aycliffe incident, which had very similar hallmarks to the incident at Hatfield. Failure to react to and remove the defects that were identified at the Welham curve or manage the risks of the delay in their removal. Once the defects were found and reported, it was down to the local maintenance team to plan for their removal. The Welham curve fell under the King's Cross Area Maintenance Engineers patch. This area had major issues with its management of rail defects. A large number were overdue. By the 1st of June, it was reported that the area had the following defects. 2H, 10 defects to be removed within 4 weeks, 7 were overdue. 3C, 66 defects to be removed within 13 weeks, 19 were overdue. 89 weld repairs within 3 months, 41 were overdue. 30 of the 54 retests were overdue, although the rail in the derailment zone was up to date. This was not helped by the system in which rail defects were stored, did not communicate with the system used to plan other maintenance works, leading to defects being missed. The biggest issue, however, was how the overdue defects were managed. Investigators found that no risk assessments were undertaken for the defects that were overdue. This meant that the risks of the overdue defects were not mitigated in any way, but instead just left until they could be removed, worsening all the time. Finally, the report found that Railtrack, the asset owner, failed to oversee the maintenance and renewals contracts of its maintenance contractor correctly. The report is damning in its conclusion of the performance of Railtrack, stating, "The shortcomings show Railtrack's inability to discharge its responsibilities to maintain a safe infrastructure and effectively manage BBRML's maintenance activities on ECML." It stated key issues with Railtrack, that the culture was conditioned to make decisions with a bias towards minimising train delays rather than the quality of maintenance, that it failed to apply management systems to ensure BBRML met its contractual standard on maintenance quality, that although several senior managers took BBRML to task over its maintenance standards, including threatening financial action, the zone director signed a certificate informing HQ that the area was compliant with the standards. This didn't have or require any supporting evidence. Overall, it was clear to the investigators that Railtrack was not putting safety as the number one objective in its maintenance strategy. Reaction and legacy. Following the incident and investigation, the repercussions on the railway industry were immediate and huge. With Railtrack not knowing the extent of the issues with rail fatigue defects across the infrastructure, over 1,800 speed restrictions were put in place. This caused significant delay and disruption across the national rail network for over a year. Some estimates have put the impact at £6 million a day. This, along with the costs of the required renewals to remove the issues, led to Railtrack as a company going bankrupt. From this, the government created Network Rail, the current infrastructure manager. It also led to the end of contracted maintenance. Network Rail brought all maintenance back in-house shortly after it was formed. The investigation made 13 recommendations around the management of maintenance, rail defects and the management of RCF. All of these were accepted by Network Rail and implemented. The Crown Prosecution Service announced in 2003 that 6 individuals were to be charged with the manslaughter of the 4 people who died during the incident. In addition, charges including manslaughter were brought against Network Rail, in its capacity as formerly Railtrack, and Balfour Beatty. At various hearings through 2005, all the charges against the individuals were dismissed, along with the manslaughter charges against the companies. Balfour Beatty eventually pleaded guilty to health and safety charges, while Network Rail was also found guilty. Balfour Beatty were fined a record £10 million, later reduced to £7.5 million. Network Rail was fined £3.5 million. To give context, prior to Hatfield, the largest fine imposed for health and safety offences on the railway was £2 million on Thames trains after the 1999 Paddington Rail Crash. When it came to the management of RCF, significant investment was made in improving the means to detect RCF and its defect. Hatfield also increased the profile of RCF, meaning it was treated with the required urgency and caution. Thank you for taking the time to watch this video. If you want to know more about railway engineering, a great place to start is our Track Component Guide ebook that is available at the link in the description. If you want a little added extra, by signing up to our email list at the link below, you'll get our free Guide to CANT ebook straight into your email inbox. Do drop any comments or queries below, hit that like button and subscribe so you don't miss a single video. Thank you.